All right, today we're talking about graphing exponential and logarithmic functions. So let's start with exponential functions. So typically we'll see them in a form like this, y equals 3 times 2 to the x. So let's graph this. It's not exactly a parent function here. In fact, usually just using 2 to the x is a parent function, but we'll go ahead and continue from here. Okay, so let's go ahead and plug in some x values to find our y's. So as we plug in -2 for x, remember that's the same as 1 over 2 squared, which is 1/4. So 3 times 1/4 is 3/4. So at -2, we are at 3/4, somewhere roughly there. At -1, 2 to the negative first, gives us 3 times 2, or sorry, 1/2, 1 over 2 to the first power, which is 1/2, which gives us 3/2, or 1.5 as a decimal. Okay, plugging in 0. Well, remember, anything to the 0 power, except for 0, is 1. So this becomes 3 times 1, or exactly 3. Plugging in 1, 2 to the first power is 2, and 3 times 2 is 6. So when we're at 1, we're up 6. And you'll start to see a pattern as we plug in our last one here. 2 squared comes 3 times 4, which is 12. And you can kind of see this nice pattern happening here, is that we're repeatedly multiplying by 2. It's almost like exponents are a way of writing repeated multiplication. Okay, but in fact, if you keep going this way, your values kind of get smaller and smaller. And in fact, if we plugged in 2 and we doubled 12, we'd be up at 24. Oops, I forgot 212, sorry. At 3, we'd be up at 24, way out of my graphing window. And in fact, we get a graph that looks something like this. Okay, so there's our nice graph drawn in, better than I can do by hand. So let's talk about our domain here, our possible x values. Well, remember, x is an exponent, and that does not have any restrictions on it. Our domain is the set of all real numbers, no restrictions. Now, our range, though, this does not actually go up and down forever. So think about if we said we're multiplying by 2 every time x goes 1 unit to the right, when we go left, we're continually dividing by 2. We're multiplying by 1/2, and this value just gets smaller and smaller and smaller and smaller, but it never gets to 0. And so here, for this particular one, our range is that y has to be greater than 0, which does mean we have a horizontal asymptote at y equals 0 for this first function. Okay, so kind of our general parent function for exponentials look like this. Here is our transformation form where we can manipulate a, right? If it's negative, gives us a reflection. If it's greater than 1, it gives us a stretch. If it's between 0 and 1, it gives us a compression vertically. We've got h, which does our horizontal shift, and it's the opposite sign of what it looks like up there in our exponent, and then k is our vertical shift. Okay, so b is the base, right, of our exponent here, and it's essentially the value we're multiplying by every time x increases by 1. So every time we go 1 to the right, we're multiplying the previous value by 2 for this problem over and over again. A, of course, is our multiplier, and if there are no shifts, so if h and k are both 0, if there's no shift at all, a also ends up being our y-intercept. And again, the reason for that is if you plug in 0 for x, b to the 0 would become 1, and we'd have a times 1, or a is the y-coordinate. However, if we are shifted left or right, or up or down, b is no longer the y-intercept. Okay, h, of course, horizontal shift, vertical shift, domain is always all real numbers, because our exponent can be any real number, no restrictions. But the range just depends on if it's a graph going up like this, then y should be greater than k. And if we have a reflection of this graph, right, it might be y is less than k. So it just depends on which way our graph is opening. All right, let's go ahead and graph y equals 4 times 1/2 to the x, which if you remember from exponential growth and decay, because both a and b are positive, this is going to represent growth or decay, and this b value tells us we're going to get decay because it's between 0 and 1. So let's plug in some of these values, and let's start with the easiest exponent, which is probably the 0 power. 1/2 to the 0 is 1, so we get 4 times 1, or 4. 0, 4 is a point on my graph. Let's plug in 1. Let's do the nice positive exponents here. 1/2 to the first power, of course, is 1/2, and 1/2 times 4 is 2, half of 4. And again, remember, this is what we're multiplying by every time we go to the one to the right. So we're multiplying by 1/2, we're cutting our number in half each time. 1/2 squared is going to give me 1/4, 1/2 times 1/2. And 4 times a fourth is 1. So it makes sense, every time we go to the right, we're cutting our numbers in half. So at 3, we'd probably be at 1/2, and 4, maybe 1/4, right? Etc. Well, it makes sense. Think about it as we go to the left then, rather than kind of dividing by 2, we'd be multiplying by 2. So I'm going to guess that we should get 8, and I guess probably 16, which would be, somewhere a little off my graph there. But let's try these just to be sure. 1/2 to the negative first. Well, remember that negative exponent is going to give me the reciprocal of my fraction, which is 2 over 1, which gives us 8. Yep, -1 is 8. And if we repeat this, again, remember the negative exponent is just doing the reciprocal here, and then it's going to square the reciprocal. So we get the reciprocal, 2 over 1 squared, which gives you 4 over 1. So that would be 16, that would be off my graph. So my graph would be coming down and cutting through here. Okay, roughly something like that, where our domain is the set of all real numbers, and here my y value has to be greater than 0. I can see it's just going to keep getting closer and closer to 0 here. You can also think of there being a 0 for h and 0 for k, and because my graph is getting closer and closer to 0 but staying above it, y has to be greater than k, which was 0. Okay, let's try another example. Here's one where now we do have an h and a k. Notice in the previous example that because there was no shifts, 4 did end up being our y-intercept, the a value. And of course, this says basically if you know that's your y-intercept, you're just cutting your value in half every time you go 1 to the right. So nice pattern to follow. Okay, here this is basically the same idea, except we do have a shift. And this is an h value of +1. Remember, h is the opposite of what it looks like. So that's actually a shift right 1 unit. And we do have a k value of +3. K is +3, which means we are shifting up 3 units. So in fact, you could just take the previous graph, move everything right 1 and up 3, and we would get essentially our new graph here. So that's probably the easiest way to actually do this, is to do the one without the shifts and then shift your points. It's generally a little bit easier to calculate or to find your points that way. So I'm just going to put in the points we had in the previous graph, which were 4, 2, 1. We'll even throw in the 1/2 there and maybe 8. Okay, so this is the previous graph. And then let's just do our shifts. Let's move them right 1 and up 3. Oops, that was supposed to change colors. Try again. There we go. Nope. Just kidding. Here we go. Okay, right 1 up 3, right 1 up 3, right 1 up 3. And move this guy right 1 and up 1, 2, 3 at that little halfway mark. And there's my graph. In fact, this time my y-intercept is up at 11. I confirm this again. We could calculate all these points. Now keep in mind our asymptote, right, which was at 0 on the green graph, has now also moved up 3. So that horizontal asymptote is actually at +3, is the value it's going to get closer and closer to as my graph continues to the right. So again, that has to do with k, and because my graph is staying above, it's not a reflection. A was positive. My range is that y has to be greater than 3. Remember, it'll never equal it. It'll get really, really close. And our domain is all real numbers. Now, just to be sure that we've shifted this correctly, I'm going to check the y-intercept by plugging in 0 for x. But we've got some extra calculations to do, right? 0 minus 1 is -1. Okay, so now I have 4 times 1/2 to the negative first power plus 3. Well, 1/2 to the negative first, that's the reciprocal, 2 over 1. 4 times 2 essentially is 8, plus 3 is in fact 11. Okay, so just double checking that we did shift that correctly. For my money's worth, I like to just graph the parent function and then do the shifts afterwards. We're considering this a times b to the x kind of as the parent function, and then just applying those two shifts. Okay, what about if I need to do something backwards, right? What if I gave you a graph and asked you to write it in this form? And notice they did not include an h and k, so we're going to say that neither of these graphs is a shifted version. We just need to identify a and b. And remember, if there are no shifts, a is our y-intercept. And b is the value that we're multiplying by every time we go to the right. So let's do number 4 here. A times b to the x. Let's figure out what we need to plug in. What's my y-intercept? A is 3. Perfect. And then what are we multiplying by every time we go to the right? Well, let's look at my values. I just went from 3. My next one is 9. Whoops, that's not what I wrote. It's 9. So when we went 1 to the right, we went up 9. Sorry, not up 9, but we went from 3 to 9. So we've multiplied by 3 maybe, right? Let's check our previous point where we went from 1 to 3. They multiplied by 3. So it appears we were multiplying by 3 over and over and over again. So our equation is 3 times 3 to the x power. Now again, be careful, you cannot combine those. Do not write 9 to the x. That is not the same, so be very careful there. Okay, what about this next one? They didn't mark that nice y-intercept for me. But let's see if we can figure out what they're multiplying by. Let's see, we went from -1 to -2 to -4. Ooh, so maybe times 2 times 2. And that looks like it's at 8, so times 2. So it looks like they're multiplying by 2. They're just starting with a negative number and continuing to a negative number, right? So I think we're multiplying by 2 for our base here. We just need to figure out what we're starting with. And we're definitely starting with a negative value. So instead of multiplying by 2 to go to the right, let's divide by 2 to go back to the left. And if I take 1 and divide it by 2, sorry, -1 divided by 2 is -1/2. That is our a value. We can use our pattern to confirm, and it does look like it's at a nice halfway point, right? Start with -1/2 and multiply by 2 every time we go to the right. Okay, this is it for exponentials. There's nothing too crazy with these, and of course we can use graphing devices and utilities to help us with those. Now let's talk about logarithmic functions. These ones tend to be a little tougher, especially to calculate their values or come up with nice values of x to plug in, especially if you're doing this by hand. Okay, now first thing to note though is our exponential and logarithmic functions are inverses of each other. And if you remember something about inverses graphically, they always reflect over the line y equals x. So for instance, and I don't know what this particular graph is, it's something, but let's pretend it's not. This is y equals 2 to the x for the one in blue. Then its inverse would be y equals log base 2 of x. Okay, these would be kind of our inverse functions here, where they would reflect over the line y equals x. Right, so if you took one of them, you swapped x and y, and then you got y by itself, you'd actually change this to log form here. Log base b of something equals something. Remember, it equals the exponent. And there you can see by changing to, when you swap x and y, change it to log form, you would get what we have below. So that's how you would calculate your inverse. Remember, algebraically, you swap x and y. Graphically, they reflect over y equals x. So whereas our exponentials had this horizontal asymptote, our logarithmic functions end up having a vertical asymptote. You can kind of see it getting closer and closer to the y-axis here, but it does never actually reach. Okay, so here's kind of our generic form, and here's our shifting form where we can do a, let's do all of our a manipulations, h and k. We have a vertical asymptote, where vertical has to do with x equals, so we're using h, the variable always paired with x equals h. Our domain, though, logs, remember, have restricted values. The inside of here has to stay greater than 0. So in this form, the expression x minus h has to stay greater than 0. Okay. Now, if you solved that equation, that's what we have on the left, right? X is greater than h. But it's really whatever values of x keep this expression greater than 0. And that's how we can algebraically find our domain for any logarithm. The range is all real numbers. This graph does continue up and to the right forever, even though it's very slow, and it does continue down forever. So the range goes on forever. It's like the domain and range got switched between exponential and logarithmic functions. Crazy. All right, steps to graphing. 1, we're going to identify h and plot our vertical asymptote. That will definitely help us identify it. H and k on these graphs, by the way, like that coordinate point, is not actually a point on the graph, but it will be kind of close to this curve. It's like h and k here would have been 0, 0. It's not technically part of the graph, but it will be close to kind of this turning point. Pick values of x that make the inside of the log a power of its base. So if your base is 2, pick values of x that are powers of 2, like 2, 4, 8, 16, etc. 1, negative, 1 half, right, is a power of 2. It's 2 to the negative first. So that's what we want to do. Let's try some examples. Okay, we got 2 examples to try here. We'll be done. Graph each log function. Find and label the vertical asymptote. State the domain and range. Okay, so step 1, identify h. Now notice there's no h inside of here with my logarithm, so h is 0, which means my vertical asymptote is x equals 0. X equals 0 is right here. The y-axis plays the part of our asymptote here. Okay, so there's our vertical asymptote. Next, pick values of x inside the log that are powers of our base. So again, we'd want to pick powers of 2. So 2 would be a good value to plug in for x. Let's go ahead and do that. This would look like log base 2 of 2. 2 to the first power is 2, so this logarithm evaluates to 1. And 1 minus 2 is negative 1. So our first point that we've calculated is at 2, negative 1. Let's plug in 4 for x. Log base 2 of 4 minus 2. 2 to the second power is 4, so that log evaluates to 2. And 2 minus 2 is 0. We plug in 4 for x. Our y-coordinate is 0. Now, the reason you want to pick 3 is because I don't know what log base 2 of 3 is if I'm calculating this by hand, right? Again, this is why I want to pick powers of the base, so there are logarithms that evaluate to nice integers or rational numbers we can do without a calculator. Let's plug in 8, which is our next power of 2. And sometimes it even helps, by the way, to list out powers of your base. Like just write it out like this and then write, your numbers. And these are the values you'd like to plug in for x, etc. So this evaluates to 3, and 3 minus 2 is 1. So at 8, we're up at 1. Let's plug in 1, log base 2 of 1. Remember, 2 to what power is 1? 2 to the 0 power. So at 1, we're at negative 2. And if we plug in 1 half, that is 2 to what power is 1 half? That's to the negative first power, right? That would move us into the denominator. And negative 1 minus 2 more is negative 3. So when x is 1 half, y is negative 3. And when it's 1/4, by the way, it would be down at negative 4, etc. It just keeps getting closer and closer to our asymptote here. And then it curves, and it does continue, even though it's slowly, up and to the right forever. So our domain is that x has to be greater than 0, where my asymptote is, because we're going to the right. And the range is all real numbers. It goes up and down forever with no gaps or holes. Okay, let's try one more here. Okay, this one, we have a different h value. So here, h is positive 1, right? From inside, remember, opposite sign. So our vertical asymptote is at x equals 1. Again, this corresponds to taking a graph and shifting it right 1, so it makes sense. kind of thinking from our previous graph, we've shifted our vertical asymptote right 1. Now I do have a k value, which would have shifted log base 3 of x up. But let's go ahead and find some nice values to plug in here. So let's think about what are some of our powers of 3. 3 to the first power is 3. 3 squared is 9. 3 to the third is 27. We know, of course, 3 to the 0 is 1. And even 3 to the negative first would be 1/3. Okay, so notice, though, I want the inside of this logarithm to equal 1 or 3 or 9 or 27. So the value of x I pick when I subtract 1 from it needs to be 3 or 9 or 27. So what minus 1 would give me, let's start with, say, 3. 4 would work, right? Certainly, 4 minus 1. So log base 3 of 4. Minus 1 plus 4 is the log base 3 of 3 plus 4, which is the same as 1 plus 4 or 5. I was running out of room to write my work there. When we plug in 4, we end up getting 5. Way up here this time. That makes sense because this graph does have a k value of 4, meaning whatever it originally looked like, it's been shifted up 4. Okay, let's try 2, because again, 2 minus 1 would give me 1. Another nice one to calculate here. So we're picking 2 specifically because when I take 1 away from it, it gives me log base 3 of 1, which is something we can do by hand. That log has a value of 0. 3 to the 0 power is 1. And 0 plus 4 is 4. So 2, 4 gives us some nice points there. And then to get to 9, what minus 1 would give me 9? 10. So I know I've given them away by kind of pre-picking these points here, but that's how we came up with them. So 10 minus 1, which gives me log base 3 of 9. I'll go ahead and do my work below here this time. 3 to the second power is 9, and 2 plus 4 is 6. So when x is 10, y is 6. Okay, and so I know I'm curving closer and closer to this asymptote. So I go this way, and then this goes up and to the right, and I slightly missed my point. We'll pretend it connects there. Okay, so our domain here is that x has to be greater than 1. We're staying to the right of this vertical asymptote at 1, and my range is all real numbers. Okay, so sometimes it can be a pain to figure out what to plug in here. There is an alternate way you can do these where you change it to exponential form, but it's a lot more steps to remember, to be honest. So this might be a little challenging, but I think we can do it. You guys are honors. We'll power through. All right, so this is how you graph logarithmic and exponential functions. We'll go through more examples in class.